So if you take a look here for us, period 456, we do a study session from 8 a.m. to 9 a.m. Totally optional. If you want, if you have an IEP or an individual education plan or for whatever, a 504 plan, you can start the exam then and then go into the exam time because you do get extra time. I'm going to record myself doing the rest of the final exam review pack. So I will be there to answer questions, but you're more than welcome to basically just look at the final exam review pack movie. That will kind of be what next week is. If you have questions, by all means, ask me. But it's basically just studying for the final exam. I did ask today, actually I asked before break, I asked my Miss Shop if you guys had her. I don't know if you would for zoology or anything, but Miss Shop, I asked her last week, she's the new science department head. What if we allow kids that have great attendance and an A or B to forego taking the final exam? That was brought up then in the day's meeting, and Mr. Brannigan said he would let us know by Tuesday whether that's a possibility or not. I think we got about a 20% chance of that actually happening. I know, unfortunately, I thought that'd be awesome. Then basically, you know, you check in with me or whatever next week, and they're like, I don't have to take the final, suckers. But we'll see on that. I will know by Tuesday of next week, or I'll push it again. I'd say 20% chance. I think that the administration, in order for them to actually go with that, would basically have to just ask themselves, like, do these teachers, you know, respect the students enough to allow that to happen? Because it has been trying times. And you know, I think that if you have an A or B in the class and you're fine with that, then I wouldn't see any trouble with foregoing the final. I don't know why they would not allow that to happen, but we'll see. It's not in my hands, unfortunately. Otherwise, I'd say, yeah, no final, sweet. All right, so let's take a look at what we have today. Today and tomorrow, we're doing periodic trends. This is a PowerPoint. I don't do many of these, but I think that since we are at home, that maybe some of these pictures will allow you to visualize it a little bit more. During the PowerPoint too, I'm going to ask questions, so please, hopefully you will help me out on that. The Wave Math practice quiz today as well. The answers are not up for that yet. I'll put that down here, probably by period 9. Yeah, boom. Don't forget the final exam review pack is up here with the answers, and I will post both the video from the 9 weeks where we went up halfway through and the new video. I'll see, maybe I can knock that out today. I don't see why I couldn't. All right, without further ado, let's do these 2 math problems and then we will go from there. So you were to find the energy from 2 to 1, and foolish me hid the other energies from itself. Here they are. So we know that 2 is the higher principal energy level. So that's negative 5.45 times 10 to the negative 19th joules. We're going to subtract from that negative 2.18. Times 10 to the negative 18th joules. Well, absolute value that. Out of these 2 numbers, which one is the highest?
Negative 5.45.
Yeah, even though it's a smaller number, since it's negative, it is higher. 5.45 times 10 to the negative 19th minus negative 2.18 times 10 to the negative 18th. We get 1.635. Times 10 to the negative 18th. Basically what that practice quiz does is it has you do a bunch of these things, and then maybe you would take this energy of the photon and then you would calculate its wavelength, which is the problem number 6 down here. Yeah. Let's see here what the best way to do this is. There we go. So when the electrons quantum leap, basically from a higher energy level to a lower energy level, it emits a photon of this amount of energy. What is the wavelength of it? So again, we're going to rearrange the equation to be wavelength equals Planck's constant times the speed of light divided by this energy. So 6.626 times 10 to the negative 34th joules times seconds multiplied by the speed of light, 3.00 times 10 to the 8th meters. We're going to divide all that by 4.09 times 10. We're not. I just copied the problem. We're going to divide all of that by 3.03, which you calculated above, negative 19th joules. Meters per second. So everything here is going to cancel out except for who?
Meters.
Meters. So again, we got to use the stupid calculator because the watch can't do scientific notation that I know of. So there's our Planck's constant. There's our speed of light. And then we're going to divide that by the energy of the photon. It gives us 6.56 times 10 to the negative 7th. Every, that's meters, every 1 meter has 1 billion nanometers. So that's going to give us 656 nanometers. If we take a look, what color is that then?
Red.
Red is correct. Take a look here. Between 600 and 700 nanometers is red. That's usually about the color of the red laser. If you have any red laser pointer, that's the color of it.
On test, will we be given that chart?
Yeah, anytime you would need something like that, you would be given it. Yeah. So when a photon jumps from any energy level to the second energy level, it makes a light visible to us. We can see that light. When it jumps from a higher energy level to the first energy level, it gives off ultraviolet radiation. And if it jumps from anything to the third energy level, then we get infrared. You know. So what you should be looking on the back of that page is the periodicity stuff. This is where we can take notes for this PowerPoint in this section. So we have to take certain ideas in mind. Your knowledge of the atom itself. We know that the nucleus is this positively charged center made up of protons and neutrons. Around that are electrons. Since the nucleus is positively charged, the electrons are negatively charged. They are attracted to that nucleus. They can only be in certain places around that nucleus because they're going to push on each other and repel each other. So around the nucleus, there's a very small volume where these things can be. It only holds 2 in that first principal energy level. And then as you go out, you can hold more electrons. You can hold more electrons. My cat is being crazy today. No. So that's basically it. Electrons around the nucleus. Now, the more positively charged the nucleus is, the more protons it has, the stronger that charge. Think about it like a neodymium magnet. If you've ever seen one of those real powerful magnets versus a magnet that's not. The neodymium is going to be able to, it has more of a magnetic force, so it's going to be to attract more, like, let's just say paper clips, than one of those like weak refrigerator magnets. So the more charged the nucleus, the greater force that the electrons get pulled in. The less charge the nucleus has, the less protons it has, they're able to spread out there more. So they're further away. So with that, let's take a look at this PowerPoint. First time sharing a PowerPoint. So we will see. I don't know how this is gonna work. Can you guys see that at all? Is it big enough to read?
Yeah.
All right, cool. So if we take a look, and I might be able to zoom it in a little bit. So on this side, we have the atomic radius. And on this side, on this axis, we have the atomic number. So we can see that we start with lithium. It might be a good idea to have your periodic table out to the side. So we start with lithium. This is 155-ish, what we call picometers. That's the atomic radius. So if you had two lithium atoms that were right next to each other and bonded, that would be like basically the distance between those two. So 150 picometers. You have 3 protons. Oh my God, I'm going to bust you. You have 3 protons and it's pulling on 3 electrons. Here we have the next element with 4 protons. It's pulling on 4 electrons. Let me grab my periodic table. That way I don't sound foolish. I believe that's boron, but no, wrong. Beryllium. I was one ahead. So we have 4 protons pulling on 4 electrons. Now that remember the nucleus is quite small, right? But now this charge is +1 more. So it's actually going to pull those electrons in tighter. And then we see here we have boron. It pulls them in a little bit more tightly. Here we have a carbon, a nitrogen, and then oxygen. And basically they're pulling them in tighter and tighter and tighter. Now the weird thing about nitrogen is you can see kind of, that's when we get each of those p orbitals in that 2p sublevel. Each one has 1 electron now. So you can see it's not much smaller. But then when we get oxygen, shoom, it goes down again. And then we ended at neon. And then what happens? Poof. Why does it go up so much here?
Because you're starting a new energy level?
You got it. We just ended 3p. This is the start of 4s. So now we have a whole new energy level. Oof, much bigger now. And then the trend, it starts again. As we increase the number of protons, the electrons get pulled in more tightly until we get to argon, and then boom, back up again, right? That's the start of the 4s, I believe. This would be the start of the 3s, 4s. And then we see that trend again, and it is a trend. Like you're like, well, those right there don't do it. Well, that's the thing. This is a trend. There are some things that we're not going to focus on that may go against that trend. So basically the atomic radius, they take and put the molecules next to 2 that they can measure, and then they take that distance right there. As we go on the periodic table, from the left to the right, we add protons. That makes the nuclear charge bigger, which pulls the electrons in tighter. So as we go towards fluorine, the radius decreases. As we go up a group, from the bottom to the top, the radius decreases. If we say we're going down a group instead, then we're adding more and more energy levels, which means that they're going to get bigger and bigger. Now here is a look at those in their picometers. You can see 1 proton, 2 protons. Even though this has 2 electrons, it's pulling them in tighter. Lithium versus beryllium. And then you can see these guys right here even get a little bit smaller and smaller and smaller. Here we have the next one. Again, boom, we go down 1 from lithium to sodium. We go from period 2 to period 3. Whole new energy level. Gets bigger again. So if we look at the periodic table, francium, probably the largest. Helium, the smallest. Now, a lot of times we don't work with noble gases with periodic trends except for atomic radii. So usually you'll hear me say fluorine or something like that instead. So on your periodic table, if you have one that you can write on, I've never found one that does this. I would not write atomic radii go increases as you go down. What I do is I make all my arrows up and towards the right, like fluorine. And then I keep the words the same. Atomic radii decreases as you go up and to the right. Don't know why nobody has ever made a graphic like that, but they haven't. So the next trend is ionization energy. So for something to ionize, that means basically it forms an ion. Now, there are 2 ways to ionize. You can gain electrons to form an ion, or you can lose electrons to form an ion. The ionization energy is the energy that it's required to take an electron from something. Now, what's taking the electrons? Well, if the nucleus of one atom gets close enough to the another atom's electrons, and it has that nuclear charge, it can grab it off of there. It can grab it off of there. Let me see if this is better. Is that bigger for you guys? Is that better? Yeah. All right. So it has the ability to pull it off there. There's a certain amount of energy that is required, though. That energy is called the ionization energy. Well, let's say you have a little baby brother or sister. They just got back from Halloween, and they're sitting there dumping their pillowcase of candy out. Which candy is going to be the easiest to take away from them? I'm not looking for M&Ms or Mars bars or something like that, but
The ones furthest away from them.
yeah, right? The ones that are furthest away from them. Like if they have a big, huge thing and they're sitting in the middle of Mount Candymore or whatever, you can be like, oh, look at the dogs doing something. And then take the ones that are furthest away from them. Well, that's what happens here as well. So if you have a big old size, big old atomic radius, it's going to be easier to take electrons away from you. Fluorine, remember, all packed in tight. Those electrons are quite close to that nucleus. There's not going to be a nuclear charge from another atom going to be able to get in there and take away an electron from fluorine. So as you move towards fluorine, up and to the right, the ionization energy increases. As you go down a group or whatever, like towards francium, the outer electrons are further from the nucleus and they're much easier to remove. So as you go up, it's harder to remove electrons because the ionization energy is higher. As you move across towards fluorine, it's harder because they're pulled in tighter. So again, I make my arrows go up and to the right, and I say that ionization energy increases as you go up and to the right. Or again, you could use as you go toward fluorine. So the way questions are asked like this is like, which one is easier to remove an electron from, aluminum or nitrogen? Which one would it be easier to remove an electron from, aluminum or nitrogen?
Is it nitrogen?
Who's got the highest ionization energy, aluminum or nitrogen? Nitrogen has the highest ionization energy. That means it's going to be more difficult to remove an electron from nitrogen.
So it'd be aluminum?
Yeah, so aluminum, it would be easiest to remove one from. Keep in mind the energy is like a requirement. To remove it, if the energy is higher, it takes more to remove it. So nitrogen, we know, is unlikely to form a cation. It's going to be difficult to remove an electron on from that because nitrogen tends to gain electrons, right? It's a non-metal. Aluminum is a metal. It would be easier to remove an electron from aluminum. Electronegativity, basically this is the measurement of the attractiveness to electrons. So whose nucleus is going to be able to attract electrons easiest? Well, it's going to be something that has its electrons tightly around it so that the nucleus can get near the electrons of another atom without interfering. And if you look at the periodic table that I gave you, the electronegativities are actually listed on there. You can see the highest electronegativity on there is fluorine with 4.0 for the electronegativity. Well, who has the lowest electronegativity on there? It's a toss-up between two of them, it looks like, but
Is it potassium?
no, potassium is pretty decent at 0.8.
Is it francium?
Francium or cesium. Yep. So it's the opposite corner from fluorine. So again, the ability to attract electrons or the attractiveness toward electrons increases as you go to fluorine. So as you go up and to the right, electronegativity increases. Here you can see francium with 0.7 and fluorine with 4.0. Notice that these guys right here up in this corner have the highest electronegativities. These are very reactive for taking electrons. They have what we call a high electron affinity. These guys over here, they're like, meh, you want my electron? Have at it, right? That's like the Tootsie Rolls in the Mount Candymore. No, I've got some pretty good candy here. Don't care about one or two Tootsie Rolls. So keep in mind that this is the group of elements that forms a +1 charge. Again, this is pretty low. This is the group of elements that forms a +2 charge. They form a positive charge because they're losing electrons. So again, I put my arrows up and to the right, and I say electronegativity increases as you approach fluorine. What do you think happens if, like, we take a sodium and we remove one of its electrons? What do you think happens to the size, the radii? You think it gets bigger or gets smaller?
Smaller.
Yeah, right? It had these electrons out here and we took one. The cool thing is if we take one from sodium, we just took the one electron that's in the 3s orbital, right? So now it's actually gone down in energy level. Now it has the same electron configuration as neon because it's lost one electron. It has the exact same electron configuration of neon. We know it's not neon. Why is it not neon? Well, neon has
10 protons. Well,
while sodium would have 11. So let me ask you this. Do you think that the size of the sodium ion would be larger or smaller than neon?
Larger.
Well, keep in mind, we now have 11 positives pulling on how many negatives?
Oh, 10.
10. So now our nuclear charge is even bigger than that of neon, but we're pulling on the same number of electrons. So what's it going to do?
doesn't try.
Smaller.
Yeah, it's going to pull them in tighter, and it's going to be smaller even. Well, let's say that fluorine comes in with its high electronegativity, and it grabs that electron from sodium. What do you think is going to happen to that fluorine when it becomes a fluoride ion? Now we have 9 protons, but we're pulling on 10 electrons.
Is it gonna get bigger?
Yeah. So when the fluorine grabs that extra electron, they have to kind of reposition themselves and they start interfering with each other and kind of pushing out. And it actually becomes bigger than the original fluorine atom. So cations are positively charged because they've lost electrons and they are smaller than the atom. Anions are negatively charged because they've gained electrons and they are larger than the corresponding atoms. Now remember, I can't do that, sorry. Non-metallic, I wanted to highlight it. Non-metallic atoms gain electrons normally, and metals tend to lose electrons. So think about that, like calcium. Calcium is going to lose 2 electrons. Now you have 20 protons pulling on 18 electrons. Whew. It's going to be much smaller, right? So this is a quick look at these. Oh, it was a quick look at these. This is a quick look at the size of this. I think I have a better one. Maybe I don't. I do. Just to give you an idea of this. Is this the last slide? Hey, that was painless. Just to give you an idea of that, if we take a look, lithium compared to the lithium ion, fluorine compared to the fluoride ion. So it actually doubled the size, right? When it lost an electron, the lithium became much smaller, not quite half the size. When it gained the electron, fluoride became much bigger. Actually, it is more than double the size. Excellent. That was pretty easy. All right, so let's take a look. Let's add on just a few little things. So we talked about ionization energy, and that's the energy required to remove an electron. So sodium, we know sodium has 11 electrons. To remove the first electron from sodium takes about 495.8 kilojoules. To remove the second takes 4,562.4. Why is there such a huge increase between here and here?
Well, isn't because like they've already reached the octet, like they've reached the full stop, so
Yeah.
they don't want to lose it.
You got it. If we lose 1 for sodium, it's reached the octet. And then we go from the 3rd principal energy level to all the electrons being in the 2nd principal energy level. Now they're much tighter. They're closer to the nucleus. It's going to be much more difficult to remove 1. Magnesium, who is in group 2A, 737.7 units to remove 1. That's the first one. The second one takes 1450.6. It's double the energy, but it's still not too crazy high. But look here, from the second electron being removed to trying to remove 1 more after that, huge jump, 6 times at least the amount, right? Boom, huge jump. So that tells us that magnesium is able to lose 2. And that makes sense because it's in the second principal, it's in the second group, 2A. Aluminium is in 3A, so it's able to lose 3. And then boom, another big jump, about 4 times as much there to remove that the 4th one. That makes sense. Aluminum tends to gain, tends to lose a total of 3 electrons. And then we have a nice little chart down here. And again, I don't know why somebody just can't make all the arrows point up and over. It looks like they did something here, here, and then let's do this weirdness. Actually, that whole thing is based on increasing. That's not that bad. So increasing in atomic radius would be down here. Increasing in everything else would be up here. All right, so these are questions that merge both of these units together. There should be a page that looks like this. It says like the group described by P2 wants to do this. So if we take a look, P2, hopefully you can identify where that is on your periodic table. This is P1, this is P2. So these elements here in the P block and the second in the P block, they want to take a charge of what? Well, P2, we only know these guys right here. What do these guys like to take a charge of? They don't have a set charge, but do you remember? What do you think?
4
Yeah, 4, right? You've heard of 10,4 oxide back in the naming days and lead 4 chloride. So those guys like to take a charge of +4. And here's the weird thing. Carbon can become a carbide ion. And it would take a charge, instead of a plus, it would take a charge of -4. So that's kind of a little trick one there. Plus or minus 4 for those guys. What if I would have said S2? S2 likes to take a charge of what?
2 plus.
2 plus. S2 would be magnesium, that'd be group 2A, right? Metals generally have more or less than 4 valence electrons and want to form cations or anions, which when formed will increase or decrease their atomic radius. So this one's the world right here. This wants you to tell a complete sentence. So metals tend to be on this side of the periodic table. Remember, all of these guys have 2 valence electrons. These transition metals, because the 4s comes before the 3d, the 5s comes before the 4d. So these guys all have 2 valence electrons. So metals tend to have, if all those guys have 2, metals tend to have less than 4. What do they want to form? What then? If they have less than 4, they will tend to lose electrons, which will make them cations, which when formed, if they lose, they will become smaller. Oh, look, what charge does S2 group want to form? Well, we already said it, +2. What takes less energy to occupy, 5D, 6S, or 4F? Well, using the periodic table, here is 6S. Then we go down to, right, 56, 57. We go down to 4F. And then after that, we go from 70 to 71 back up to 5D. So which one filled in first? That would be 6S. Group 4A likes to take a charge of, well, we said already up there, plus or minus 4. And has how many dots in its dot notation? Now this is actually going to take us into what we're starting in January. This is called Lewis dot notation. So you draw the symbol. It has 4 valence electrons. So we give each side 1 before we give any 2. That's basically how we make our octet. If this were all filled, it would be fulfilling the octet. So if I were to do sodium, it only has 1 valence electron. If I were to do magnesium, it would have 2 valence electrons. So carbon, each valence electron has 1 dot. So carbon would have a total of 4 dots in the dot notation. It's described by the letter and subscript. Well, what block is this? This is the P block. How many in? 1, 2. This would be P block and the second in it. And its radius does what when it forms anions? That's a tricky one. because they put that there. It's plus or minus, but it's saying it's forming anions. That means it's gaining electrons, so it must be getting bigger. Nonmetals want to gain electrons and form anions. When these ions are formed, the radius will be bigger. Almost the same question there. The backside of this has some very similar questions to that. And then down here, basically, it's asking for like, what is the identifier? You can't see that. What is the identifier for like sodium? Well, sodium, its last electron configuration combination would be 3s1. That's kind of what it's looking for here. Here's the opposite. Who's at 6s2? Who's got their periodic table out and can look down and find 6s2 real quick?
Barium.
Barium is correct. And basically, those exercises there, they're trying to basically get you to your mind focused on being able to do all of those electron configuration stuff with the periodic table. So for tomorrow, I suggest you go down through 7 through 13, and then maybe pick the evens or odds on the back side of this, and just to get you a little bit of practice through it. And then we'll go over that tomorrow in class. I'll show you the answers to it. We'll discuss it. And that will complete our first semester of Chemistry X.
Wait, Jackson?
Yeah.
You want us to do this page and the back side of it, and then that's it?
Yep, that's it.
Okay, cool. Thank
You
you.
don't have to do the whole back. I mean, it's a lot of repetitive stuff. So if you just want to do the evens or odds, that's fine. On the back. I stopped here because 7 through 13 here really goes over what we talked about today. So I want you to kind of look over those notes that we discussed a little bit more. But yeah, so I do want you to do 7 through 13 complete, like every one of them. But then the backside, even or odd, don't care. Questions?
Are we doing unit tests over this?
Are we doing a what? Unit test? What we said is that this is kind of heavily, so if we were to look at the final exam, about 20% of that final exam is this stuff. So it's heavily weighted on the final exam. So if we don't have a final, then meh, right? Yeah.
On Canvas for today, there's a wave math practice quiz. Should we do that?
Yes, definitely. That's the math that we just did. And I
Okay.
said I would put the answers for that up there after probably by period 9 today. Basically, you can expect one of those types of, at least one of those types of formulas to be required on the final exam. If we have a final, right, Dawson? Any other questions? That's all I got, guys. Get out of here. Hudson, I need you to do more. Oh, he left. It's going to tell him he needs to play more. Get that level up.
Mr. Jackson,
Yeah.
do you think you could go back to one of the slides on the PowerPoint? I just want to take a picture of it.
Yep, no worries. Which one?
It was the first one about ionization.
Energy?
Yeah.
Tell you what, yeah, I'll just let you do that. I was going to say, I guess I could put this PowerPoint up on the thing, but
You can do that too.
actually it's in the Zoom, but here you go. Can you see it?
Yeah.
Yeah.
Thank you.
You're welcome.
Have a good one.
You too.